So it is asking for some permission. Let me figure it out. I have to quit and reopen. Okay.
Okay.
Oh, it's a recording, right? Ah, shit. Yes.
Okay.
Can you give me permission now?
Yeah. And given the permission, can you try?
Yeah. Let me try.
Yeah.
You can see.
Yes.
Do you see the full screen mode? Or the presenter view?
I don't know if it's because of my setup. I'm seeing, yeah, now it's full screen. Yes.
Okay. Okay.
Yeah.
Good. Probably there is a delay.
We will start at 5.
Sure. Sorry, I don't use Zoom very often, so I'm trying to find where my camera is.
It will be downside, most probably.
Yeah. I will do stop sharing for a moment and try to see how the camera I can turn on.
Yes. Okay. Yeah.
Can you see my screen?
Yes. Yes.
Do you see my pointer or you don't see my pointer?
I can see the cursor moving. Yeah.
Okay, that's it. Yeah. So this is part of ECE department?
Yes. I mean, part of CNI. Center for Network Intelligence. So
Okay.
on our organization.
Okay.
Okay, we will start.
Sure.
Hi, everyone. Welcome to Network Seminar Series hosted by Center for Network Intelligence at the ECE and RVCCPSI. It's my pleasure to introduce today's speaker, Dr. Subrata Mitra. He will be speaking on redefining caching for generative AI. Dr. Subrata Mitra is a senior research scientist at Adobe Research, Bangalore. His current research lies at the intersection of computer systems and machine learning, with a focus on efficiency and scalability. Previously, his work primarily addressed improving the performance and reliability of cloud and distributed systems and improving scalability of big data processing and recommender systems. His research contributions include approximately 40 papers published in top computer system conferences. He also serves in the PC of several major conferences. He received his PhD in electrical and computer engineering from Purdue University, MS in computer engineering from University of Florida, and BE in Electronics and Telecommunication Engineering from Jadavpur University, Kolkata. Prior to Adobe Research, he had spent time as research interns at Microsoft Research, AT&T Research, and Lawrence Livermore National Labs. Even prior to that, he worked in software engineering roles at Intel and at Randall on new product development and on electronic design documentation automation. We request the audience to keep your microphone silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box, and we will relay your questions. Over to you, Dr. Subrata.
Thank you so much for the kind introduction, and thanks for inviting me. So today I will talk about reinventing the cache for generative AI. And before I start, I guess this is a must-have diagram for any presentation on generative AI. So this is a nice sort of website where you can visualize the growth of different type of generative models across various timelines. So I just took a snapshot between 2015 and 2024. And on the x-axis is the timeline, y-axis is the number of parameters that these models have. And as expected, we can see a huge growth in the model size, which is not a new news anymore. And we can see that there is a bunch of models coming from industry and then also some models from academia and academic collaborations. So while the sort of the training of these generative models and how resource intensive these trainings are is sort of well known, and more and more this becomes more power and energy constrained and sort of course extensively hugely expensive. Inference of these models are also extremely compute hungry, and because these models are often used in various user-facing applications, how do we optimize these models for lower latency and lower cost, and maybe higher throughput for serving is of interest. So before I move on, this is like my brief agenda. I will give a very brief overview of the generative models just to give little context of how they work. And then as the title says, our work, at least the focus of this presentation is use of various forms of caching for generative AI. So I will motivate why caching and what is special about caching in case of generative AIs. And then I will go over two of our very recent works. One was published in last year in NSDI, which is targeted to text-to-image diffusion models, which is a class of generative models, as I will explain in the introduction. And then one soon to be published in SIGMOD 2025, which is targeted for caching for LLMs for sort of targeting towards more text-based AI assistant applications. And then I will have some discussion on future directions and we'll conclude. And feel free to stop me anytime if you have any questions. Just a very brief overview of when we say generative models. There are various types of generative models. In the past, before the recent popularity, people have extensively explored GANs and VAEs, and then there are flow-based models. But over last, I would say like 2-3 years, most of the discussions are going around only two class of generative models, mainly diffusion models, which was extensively being used for text-to-image generation. And second one is transformer-based models or autoregressive models, which is mostly used for large language models of today. In this presentation, I will mostly focus on these two models, and our works are tailored for these two models. So just to give a brief background on what are these diffusion models. So a diffusion process is when an image is noised up progressively during training until it becomes almost like a Gaussian noise, and then the training process learns how to denoise that Gaussian noise to get back the same image. So that is the training process that happens during diffusion models. After the training is done, basically these models, which are deep neural networks, learns given a Gaussian noise and a text prompt, how to denoise that Gaussian noise to create a faithful image which captures the essence of the prompt. And this denoising is done through several steps, and there are various names of these steps. These are called time steps or sampling steps or denoising steps. But essentially, every time this Gaussian noise is denoised a little bit, then it is conditioned on this input prompt and further denoised and further denoised. So this was basically the main technique with which the original text-to-image models was working until last year. Very recently, there is a little bit of change in this process. Instead of a previously used particular type of model, which was called UNet, now these are being the transformers, which is the dominant architecture for LLM, are also being used for text-to-image models. But essentially, these diffusion models, this diffusion technique remains the same. And just to highlight, even for the inference, what is the challenge? So if we see how the hardware is evolving and there are more and more powerful GPUs are coming. Here, there are only 3 GPUs that we are showing after so older one is V100, then A10 or some version of that, which is available on AWS called A10G, and more powerful A100s. And now there are even more powerful H100s and all. So these GPUs are significantly more powerful compared to the previous generation, but the model size and the parameter size of the model are also increasing, as I had shown in the first slide. And as a result of that, we can see even if the hardware is becoming more and more powerful, the latency of image generation also is non-trivial. For example, if we look at a smaller model that would have taken sort of very tiny amount of time on A100, if we try a much larger model, so some of these references are from last year when the paper was published, which is called SDXL, which is Stable Diffusion XL, which is a much bigger model. When run on one of the most powerful GPUs of last year, which is NVIDIA's A100, was taking significantly more time, up to 6 seconds, even on this more powerful GPU. So, so models are sort of playing a catch-up game, or sometimes sort of overshooting the hardware development that is happening because models are becoming more and more complex. So now to give quick brief background on the autoregressive models or LLMs, now it's sort of almost everyone knows how LLM works in this era, but just to still give some background, LLM is an autoregressive model in the sense that when we basically give an input prompt to the LLM, it predicts the next token or next word. There is usually it's in terms of tokens, but let's say next word, and then the next word is sort of appended with the previous prompt and passed to the LLM, and then it produces the next token, and so on and so forth, as you can see in the left bottom corner. Now, LLMs are humongous compared to diffusion models, and therefore it has humongous computational needs even during inference. LLM inference, I'm not showing here explicitly, has two phases. One is called prefill, and another is called decode. So prefill is the phase where whatever you pass to the LLM, we call context, that LLM consumes and creates a certain intermediate state. And then it starts to generate each word at a time, and then feedback generates this word at a time in autoregressive mode. So that generation is called decode. So if we analyze the computational characteristics of LLM between prefill and decode, we can find that prefill is significantly compute bound, meaning whatever sort of weights or parameter it loads from the memory keeps the computational cores of the GPU extremely busy, and it doesn't wait much for the memory transfer after certain optimizations were done already. And then decode is significantly memory bound in the sense that because every time it generates a word, and then after that goes back to the model, certain amount of transfer needs to happen between the GPU memory and the GPU cores. GPU cores do not remain busy all the time. Since in our work we will focus primarily on the prefill part of it, on the bottom right corner, I'm just showing the scalability problem of prefill in these generative models in LLMs. So you can see that as the prefill length increases, the time for completion of the prefill significantly increases. So this is because the prefill computation is extremely complex, and then it is sort of order of n square in terms of the number of input tokens. And often we don't talk about only one handling one prompt at a time, because production inference system will probably handle a lot of prompts at a time coming from different users. So there is some sort of a batching that is used, and we are showing also, if we use batching, how the time increases because of the compute becomes extremely saturated at that point. So now, again, just a very high level background on what we mean when we say AI assistants. So AI assistants is typically the way it is used in many of the production use cases, is a way of using LLM backed by something called Retrieval-Augmented Generation, or RAG. So LLMs have their own knowledge, which is infused in the LLM during training, often called global knowledge. And then in various scenarios in production, when we try to use the LLM in the bounds of that product or the knowledge base of the product or the domain, usually a set of knowledge chunks or documents that are part of the knowledge of the product or the domain is passed to the LLM. and then LLM uses those documents with the user's question in conjunction to produce an answer that helps in user in certain way. So on the sort of left side, I'm showing a very high level overview of the flow of this. So when a user question comes, usually there is a component that tries to understand what this question is, usually by taking help from the prior conversation with the user. So in question rewriting, this question of the user is given proper context so that it can be independently understood. And then based on this current context of the question, the relevant documents from the knowledge base or chunks are retrieved from a knowledge database. And these users' question along with these document chunks are passed to the LLM, which then generates the response that goes back to the user. And this process is called Retrieval-Augmented Generation because we are augmenting the generation by retrieving the relevant documents, which is supposed to sort of overpower LLM's own knowledge that it might have acquired from the global knowledge during training. There is also a similar flow that happens in another very popular paradigm, which is called in-context learning or ICL. In that case, for this given question, instead of document chunks, a set of examples are selected, and then those examples are passed along with the question and maybe along with some documents so that LLM learns how to handle this question and how to handle some similar questions are the examples that are retrieved and passed to the LLM. So now, before we go deeper, there has been a lot of work already. I mean, huge number of work, so much so that it's probably like calling out each and work is difficult. So I'm grouping those works in certain categories in both diffusion models and LLM inference optimization. So for diffusion models, the first box are the traditional sort of optimization that are done with ML models and deep learning models, starting from quantization, which tries to change the precision or the representation of the parameters, making them smaller and smaller, or reducing the precision so that they can be loaded from the memory faster, and in some cases can be inferred with lower precision so that the memory footprint and the latency becomes lower. Pruning is like we can prune traditional, like a lot of unwanted parameters that are not needed, and distillation is we use a bigger model to train a smaller model so that the model size reduces. So these are nothing very specific for diffusion models or LLM. Of course, the exact technique might change a bit, but these are broad category of things that were being used even outside of these models. For diffusion models, I will double click on this part more in detail in some future slides. But essentially, what I said is that the sampling process that makes an image from a Gaussian noise conditioned on an input prompt, and that is the most time-consuming part of the diffusion. There are several works that targets how to make that sampler more efficient, how to parallelize that sampler, and all of those techniques. And then there are model serving techniques, which basically sort of takes a broader view of given a model or sometimes a bunch of models. How do I choose the suitable model during inference? How do I scale out the number of computation GPUs as my load changes or increases? And for diffusion model, there has been some work. How do I sort of split an image into multiple parts and then sort of distribute those parts across different GPUs, and sort of so that I can sort of combine these different parts into a coherent image later, but sort of parallelize the inference in a distributed manner. So similarly, in LLM inference, also there has been a lot of work. Again, the first block is sort of similar: quantization, pruning, and distillation. Then there are a lot of work that targets the most compute-intensive part of this inference, which is called attention calculation. And I will give a overview of what is called attention calculation. So there are few very notable and very popular techniques that are used today are called flash attention, which basically reduces the need to go back to the memory repeatedly during attention calculation, and then paced attention sort of borrows some ideas from operating system to manage how some of the intermediate sort of tensors that are generated from LLMs are managed and laid out in the memory for efficiently using during the computation. And sparse attention basically tries to reduce the overall size of the metrics on which the calculation is done so that the computational complexity reduces. And for LLM serving, on the side of LLM serving, there are various techniques that tries to basically mix and match these prefill and decoding phases, breaks the prefill into certain lengths so that they can be efficiently overlapped across users for efficient utilizations of the GPU, because as I said, prefill is compute bound and memory and decode is memory bound. So they try to overlap those so that all the resources are used properly. Speculative decoding is a technique where sort of you can use a smaller model in conjunction with a base model or larger model to increase the speed during generation. And there are various works on parallelism and batching that tries to basically look at how do you distribute these tensors across various GPUs, how do you batch requests so that you increase the throughput of the system and able to handle higher load. Many of these techniques for LLMs are implemented inside the most popular open source library that is used for efficiency, which is called VLLM. And if you are interested, you can go to this VLLM project and find out more on this techniques. So now let's sort of understand why we are interested in caching. So various techniques that we have, basically, we talked about are tackling various aspects of the computation. And our observation is that for both diffusion models, it started with diffusion models and then later we extended it to LLMs, is that when we sort of treat these models as a system, not as a standalone model, and that these systems are basically deployed and will serve not just one query, but various queries across the time period, probably from various users, we can take advantage of this fact and make those systems more efficient by caching or reusing, right? But there is a catch here, which makes this caching different from the traditional caching techniques, is that many of these prompts or building blocks that model takes or model generates are not exactly matched across the users. And so therefore, there is a need to understand how do we operate when things don't exactly match, and how do we still take advantage of these limited matching across users and still reduce the computation during inference. So here I'm showing some analysis that we had done across user prompts from a very popular stable diffusion Discord server. So what we did is we sort of clustered these prompts using DB-scan clustering algorithm. And we sort of took the top 10 clusters And we saw that out of those top 10 clusters, out of the clusters that are top 10 today, what fraction of those remain in the top 10 in the subsequent days, probably up to 18 days or something. Yeah, like more than a week. And these values at the top basically shows that how strictly we treated two prompts in terms of their similarity. So the lower the value, meaning the stricter we were. So the top left corner is where we didn't consider two prompts as similar unless there is exact match between them or very high match. And then bottom right is where we relax this constraint and sort of considered what does similarity mean. So interestingly, if we see the top left corner, we will see that, and the y-axis, we are basically plotting sort of the probability to remain in top 10 as over next several days. So interestingly, we can see if we are too strict that if we are looking for exact matching of prompts, then something what is popular today across users may not remain popular in 2 days. Actually, the probability drops quite a bit in the next day. But as we relax this similarity, meaning if we allow for two prompts to go into the same cluster, if they are slightly more dissimilar, this reuse potential increases. So as you can see, the reuse potential increases across like as we move from epsilon 0.01 to epsilon 0.05. And what does this mean is that if we relax the similarity a bit, then we can reuse these prompts in some way in future generations. And how do we reuse is a technique that we'll sort of go over. In relation to this, we just had one more plot, we try to understand how does the intra-session similarity for the same user correlate with inter-session similarity across different sessions. So we see that user tends to try very, very similar prompts within the session, but slightly different the similarity reduces across sessions, which is just another nice observation that we had. So similarly, on the LLM side, as I said, the retrieval-augmented generation is one of the setup that we are targeting. If we look at what are these document chunks that are being used across different queries, we see a heavy tail distribution. We see that there are very small number of document chunks that are repeatedly being accessed by queries. And in the current technique or in the current way they are dealt is every time a query is looking for a chunk, the whole text of the chunk is reprocessed by the LLM. And then these attentions are calculated, which are very compute intensive, and then an answer is produced. Actually, if we look at, we actually did some more digging and we looked at various prompts that go into these LLM across various scenarios. And we tried to find out what fraction of these input that go as context to the LLM come from these RAG chunks. So you can see that there are these different colors that are showing different type of inputs that constitute the context that goes into the LLM. We can see that often these RAG chunks are consume large amount of tokens or the input context that goes into the LLM. So therefore, if we combining these two observations, if we can somehow reuse these RAG chunks across generations, we can probably save a lot of compute and latency and improve the efficiency of the system. So with that, I will go over our work that targets diffusion model using approximate caching, which was our NSDI work. And these are from Adobe Research, one of the co-authors actually now is doing PhD in UIUC. So just to, again, as I explained, diffusion model is taking a random noise, Gaussian noise, pass it through a deep neural network that iteratively denoises it and makes a final image. And as I said, there are two class of techniques. One is sampling optimization that reduces these original 1,000 steps into very less number of steps by doing a lot of optimization. The numbers that I had shown before, that SDXL takes 6 seconds on A100, is actually after all these optimizations were done, and it still takes 6 seconds on A100. The other, as I mentioned, there are these traditional techniques of distillation, pruning to make a smaller model out of this large model. And often this smaller model loses certain quality, but it is faster. So again, quickly, if we treat this setup as a system and we leverage across users, we can probably make this reuse of computation across users and save a lot of compute. So our technique goes with a few key observations. So when this different denoising step happens on a Gaussian noise, we can see that we observe that different aspects of the image form during this denoising phase. For example, during the early denoising step, the color or the structure of the image forms in the latent representation. So we'll call these intermediate steps as intermediate noise or latent representations, depending on the context. But these things are formed, and then there are some final detailing that happens during the final denoising steps. And depending on what was the original prompt and what is the new prompt, these things may or may not be changeable across after certain denoising steps is passed. So further, we can see that maybe initially, when only certain things were formed, this representation might look a bit similar, but as more and more denoising steps happen, the distinction between different prompts make its effect on the final image, and then the image becomes largely distinct, although they can have similar color palette and similar sort of objects placed in the similar coordinates in the image and things like that. So with this observation, basically, the approximate caching, what it does is that it tries to cut some of the initial part of the denoising step by directly reusing the representations, intermediate representations from another generation that had happened prior to this prompt, and then basically take that intermediate noise directly from some other prompt, and then condition that previous intermediate noise with the new prompt and tries to generate the final image. So essentially, if there are n denoising steps that a regular model would do, then if we can sort of skip the initial k sort of steps, then we can reduce the computation cost of or computation time and cost for these denoising of images. And you can sort of see that we can calculate the computation saving, which is in proportion to like k over n, and each k is basically we call hit rate, which basically gives us a hint of how usable a denoising step is if it is collected at denoising step k. So as you can see from the previous example, if we are collecting a if you are collecting a intermediate noise from a very advanced k, meaning when it is almost final, it cannot be reused across different prompts because it is already sort of almost written in stone, and it will not change much if we condition it with the rest of the denoising steps that is left. But if we take something to go in the extreme, when at the Gaussian noise level, then everything is reusable, but the K will be almost zero because we have to basically run the full denoising after that. So there is no denoising step, computation saving. So the whole sort of heuristic that we build is how do we navigate this hit rate or manage this hit rate and K so that we get some meaningful saving of this approximate caching. So some examples we can see again, if there was a original prompt, which was a white horse grazing in a green field, we can probably, there was an original prompt that was brown horse grazing in green field. If you are using a K is equal to 10, meaning we took a noise from this prompt after 10 denoising steps and then condition it with this prompt from K is equal to 10 onwards, or K is equal to 11 onwards, then we can reproduce a white horse from that noise. But as we do it later and later, we might not be able to change it. For example, the same horse, and we are trying to change different aspects here, the color and here the activity the horse is doing. Here we are trying to change the from horse to a bear, and we are trying to change the background, and depending on at what K we are using and what is the similarity between this original prompt and this prompt, we may or may not be able to change it. So based on this observation, we basically created a heuristic that profiles a sample taken from the target sort of data set or the target scenario, and understands that for different similarity scores across different prompts, at what K we can still use the prompt and get a high quality generation from the intermediate noise. So as expected, if the similarity score is very high between the original prompt and the new prompt, then we can basically take very advanced K is equal to 25 for out of 50 denoising steps and still generate a very high fidelity image. And here high fidelity, our definition is more than 90% of a target metric, which is a peak score for our example, which is a metric that correlates the generated image with the human perception. So it is basically trained on a lot of human annotated data, and this can be used to measure how good the image generation is. So, but as the similarity score becomes lower and lower, we need to take these noises from lower K, so that we have enough room to condition it for the target prompt, and then we can make sure that the generation is high quality. So based on this profiling, we could basically create this heuristic. We can basically create a logic between this similarity score and the corresponding K that can be used for that target domain. And that is essentially the heuristic that we use for our work, and to basically reuse the noises across different prompts. Now, we store these noises in some file system, and for that it takes up certain storage. And to make this storage or this cache management more efficient, we developed certain further heuristics. So we start with a fixed amount of storage for these intermediate noises. And as long as we have empty spaces, we can keep on storing these intermediate noises from all Ks during generation. Or actually, we do not store from all K, we store from 6 distinct k values out of 1 to 50. And but when there is basically a when there is not enough space left, then we have to evict something, and we have to make room for this new noise. Now, for that, we use a slightly different eviction policy, which is a slight modification of the classic least recently used eviction policy, because here the importance of a intermediate noise is not only depends on how frequently it was used, but also how much benefit it can give in a subsequent generation when it is used. So, for example, k is equal to 0 can be very frequently used, but will give almost no saving. And then a very advanced k can give very high savings, but may not be usable across very large number of prompts. So we try to balance that by just multiplying by the potential saving from k and then the frequency of usage. We call it LCBFU, and that is the eviction policy we use. And our paper has evaluations that show that how we can increase the computation saving over this LRU or least frequently used by using this technique. Now, just to give a quick background of overview of this NIRVANA pipeline. So when a prompt comes, we generate an embedding using CLIP, which is a metric that captures converts this prompt into an embedding. And then we basically look up if we have a similar embedding in the database that keeps this embeddings of the previously generated prompts and does a approximate nearest neighbor search. If we find a suitable similar prompt, then we use the heuristic to find the appropriate k for the previously generated prompt and retrieve the noise from our noise storage cache, and then start from that noise and do the rest of the generation and generate the image. In case we do not find that match in the vector database, or the match is not very similar, then we basically fall back to the vanilla generation and generate the image. Now, there is a slight amount of overhead that is there, because for every image, we are looking up in this vector database whether there is a match, and this is maybe a network connected vector database. So there is this latency of reaching it to the database, it's querying and finding and responding back. That might add some additional overhead for each prompt. So to avoid that, we basically use a predictor, which is basically a 1 plus SVM anomaly detection kind of predictor, which basically can give us a hint whether we are likely to get a match or not. This in the exact caching scenario, this will be analogous to like Bloom filters that are used to find if there is a possibility of a match, but that is for exact match. For here, approximate caching, this is more of a predictive match. So this is the overall pipeline. I will quickly go over the results. So you can see that in the blue, these are the original prompts and the original image that was generated. And on top, we are basically using this noise from this image from certain steps like K, and trying to use this noise to generate a new image for the new prompt. As we already discussed, we can see that as we have more similarity between the new prompt and the original prompt, we can use higher advanced K. But if those are not very similar, then we on the left, for example, we have to basically use a lower K, and then we can still generate a faithful image. So this is the qualitative evaluation, and then there are a bunch of quantitative evaluation across various benchmarks. We can see that there are 3 different metrics: FID lower is better, CLIP score and PIC score higher is better. And the baseline is vanilla, which is basically the raw model, which we are optimizing using approximate caching. And we can see that we can be very close in terms of quality with this approximate caching with the vanilla model quality. And we also did some users study how many users, what fraction of users said yes or like the image generated using approximate caching versus the vanilla model versus another sort of baseline, which is called GPT cache, which basically just caches the previously generated images and retrieves the images based on similarity. So we can see that we are very close in terms of user liking for the image generated using approximate caching. And some system metric, we are showing that how we can use throughput. We can increase the throughput by 1.25x if we use approximate caching. So there are two lines. One, if we are using like a fixed cache with eviction, and then another is increasing cache, meaning we are not evicting, we are just growing the cache across generations. And we can see that throughput increases. On the right, we are showing how much cost we can save because there are now additional components coming from the vector database and the elastic file system that is storing the intermediate noises. And if we include all those costs and use the pricing from one of the leading cloud providers, we can see that even with the fixed cache and with approximate caching, we can save up to like 20% of the cost. So this is sort of the efficiency aspect of approximate caching. So for the interest of time, I will quickly go over to the next part unless there are any questions. Okay. So
Yeah, one quick question. In this caching, when you select a particular cache, is there an option to backtrack? That means if you do you find that the result is not as good as you would expect, then do you do that correction at the last stage, or can you backtrack and select a different cache?
So it is, so practically it is a very difficult problem to, I mean, other than that metric that I mentioned, the pick score and those kind of metrics, it is very difficult to judge during inference how good image is unless we are looking for a feedback from the user, thumbs up, thumbs down after the image is generated. So we don't correct during the generation, but if a user do not like the generated image, then we can always fall back to the vanilla flow during the subsequent generations, because it's not a very reasoned or I mean there is no verifier to be exact that image that was generated was exactly what the prompt is for, but we can actually use the pick score as a signal and maybe correct. That will have some overhead, but currently we are not considering that flow. So these results that we are showing is aggregate result. So that means there will be some cases where the generated image was bad, and in many cases it will be good. So it aggregates across those dimensions.
Okay. So because in conventional caching, you know whether you have a cache hit or not.
Yeah.
So there's no equivalent of or measure of quality at the intermediate stages.
Yes,
Is
yes.
that correct?
That is one of the challenge. Yeah.
Thank you.
Yeah. So now we extended this to LLM, this idea, and this is basically, we call it cache graph. So very quickly, we already discussed the attention computation. So just to double click some more. So the attention calculation that happens is basically a token when we compute the intermediate values for our token. The attention computation, which is called causal attention calculation for LLMs, looks at the previous token that comes before it and calculates its value. And during this example, like once upon a time, when A is calculated, it looks at once upon, and then when the time token is generated and before generating the next token, the time looks at these previous tokens like once upon a time, once upon a, and then calculates the values. And you can see that when time is looking at once upon a, there is no need for these previously calculated values, which goes from A to once and A to upon, because those were already calculated and cached. So this is basically called KV, key value caching, which is used in all efficient models of today, which uses these during a generation for a particular prompt. So again, now this is just in one layer. If we see how RAG is used in case of LLM, the same, some documents goes into the input and the question comes, then the question basically attends to the tokens in the document, and then this attention calculation keeps on happening across various layers. For example, for Llama 32 layers, and then finally the next token is generated. So this is the vanilla flow. Now, I already showed the computational bottleneck, but one obvious thing might be that these, since we have so high hit rate for some of the these chunks, why don't we just cache these chunks as it is, right? Now, because of this causal attention calculation, the calculation will change if the ordering of these chunks change. For example, if this blue chunk comes before the gray chunk in another question, then the actual computation of the value will change, and then that can change the answer. So now we analyzed how many of the actual prompts we can still use the cache as it is, if we do not if we only want to cache when they are strictly in the orders, which is called prefix match. As we can see that if we are basically considering one document, then of course it is being used every time it is used, we can use it. But if we are talking about RAG that retrieves 2 documents, 3 documents, and up to 5 documents, then the effectiveness of exact matching of prefix matching goes down, because there is very little probability that across the usage of the same documents, they will be coming in the same order. And this order is decided by the similarity of this question and the documents, and some search is done to find out in which order these documents should appear in the input prompt. So this is one concrete example. Let's say there are 4 documents. Sunlight scatters in atmosphere, blue light scatters the most, red light scatters the least, and shorter wavelength scatters more. If there is a question, why is the sky blue? These 3 chunks will be needed. And if they are retrieved in this order, then why the sky is blue will attend these chunks in this order. But because we had already seen this chunk sunlight scatters in atmosphere previously, doesn't mean that we can just blindly use its cache to answer a question, why are sunsets red? Because in this case, it might have appeared in the sequence for the input. And if we and in this case, the intermediate value of it was already contextualized by what was appearing before, which is the blue chunk. So the intermediate value is already sort of corrupted for it to be used in a different context. So how do we make sure that we can still use the chunks across different generations? So basically that is what the design of Cachecraft is. So what we do is that we store these chunk caches in a cache store, and then we sort of score these caches based on how much they were influenced by the caches before them. And based on that factor of influence, we decide whether the cache can be used in the current context or not. So to be more precise, let's say we are now looking at the even though every calculation happens at a token level, let's say we divide them at the boundary of the chunks. And then within the boundary, we calculate the intra-attention, meaning what are the tokens attending to itself within the same chunk. So this will not change. It will not change depending on where the chunk appears in this ordering, because their relative position is going to be the same. But what will change is how much this one token gives attention to the tokens that belongs to a different chunk. We call that inter-attention. So by this ratio of intra-attention over inter-attention, we can find out that whether how much influence the tokens in the chunk was influenced by the chunks, the tokens from the prior chunks, and based on that influence, we can calculate whether the chunk is sort of pure or it is sort of corrupted. And then based on this sort of marking of pure and corrupted, we decide whether the chunk can be used or not in a new context. So corrupted doesn't mean we cannot use that chunk. Corrupted just means that we need to fix those corruptions with some additional compute after we use the cache, and that basically requires some thin layer of computation. So for the interest of time, I will not go into the detail, but if you actually plot these attentions, inter-attention versus intra-attention for different chunks and different questions, it can be seen that the distributions are very non-overlapped if they are not influenced by each other. And in that case, they can be safely used, and the answer that is generated by using the cache is largely correct. But if we see that the distribution of attentions between inter and intra-attention are very overlapped, then we have observed that the result of the query that is used, that is created using this attention, using this cached attention, gets corrupted, and we get a wrong answer as well. So based on that, we basically, as I said, if they are very separated, we use directly. If they are highly overlapped, we do not use. We would rather fall back to the original tokens. And if they are partially overlapped, which is the case for most of the cases, we'll identify which are the tokens that are influenced by the tokens in the other chunks, and only dedicate computation to fix those tokens, and would not compute anything for the tokens that are not affected. And that is essentially the strategy of this cachecraft. Again, slightly more systems-oriented technique is that now we are storing these chunks in the memory. We first store them in the GPU memory. If GPU memory is not available, we move them to CPU memory, and then subsequently to SSD. So far, in any practical cases, we didn't have to move it to SSD, but that is the design that we can handle. But now, when we actually need to use them, we need to load these chunks from these memory to the GPU. And if we just wait for their loading, then we basically pay the price of this loading overhead, which is the baseline case. Like these are the loading times of across these intermediate cache across the layers L1, L2, and only all of them are loaded, we can start the computation to fix them, which is the bottom L1, L2. Better might be that as soon as we load some of the chunks, layer-wise chunks, we can start the computation of that. And even better than that would be that as soon as that we can basically preload the chunks cache for the layer that is needed. But essentially what we do is the last line is basically we try to find out where the chunk is and how long will it take to load in the GPU using this T load, and what is the time that it takes before it is needed for the computation. So based on this ratio, we basically decide that up to which layer that we should load in the transformer, these caches, before the computation can start. Now, this loading can be done when these chunks are waiting in the queue itself, because in a reasonably loaded system, the chunks are not really waiting standalone. They are waiting in the queue, and when they are waiting, we know exactly what are the caches that are needed for these chunks. We can basically overlap these computation with the loading and we can basically pretty much load the chunks that are needed before they are needed to be used by the computation. Yeah, so for the interest of time, I will just quickly go over the quality results. So y-axis is the quality, and this Rouge 1 F1 score, which basically measures how good the output generation is compared to the vanilla generation. Higher the better. And it is usually said that anything greater than 0.6 is better. But the interesting thing is that these are different baselines, and with different amount of dedicated token recomputation to fix these caches, we are sort of at the Pareto optimal in this setting. So that means with the given amount of computation, we can produce better quality. And we did some, I mean, there are a lot of other experiments in the paper, but if we look at two setups where we basically load two different sized LLM, one is small on the left, one is large at the right, and basically stress test these LLMs with different types of load, we can see that we can improve the throughput of the system significantly, and also reduce the latency by up to 3x. And the quality for all of these experiments is about 90% Rouge 1 F1 score with 30% recomputation, which is the last bar. And the general thumb of rule is anything greater than 60% is considered good. So with that, I will basically conclude the main part of the presentation. There are a few future directions that we are looking at Adobe Research. Any questions at this point? Yeah.
So one question, when you're searching amongst the cached values, again, like probably through the embeddings, are you using any specified data structures? For vision, you said
for the previous one.
For the previous one, you said you use some vector
database. Yeah, approximate nearest neighbor. Yeah.
Okay, and for the the LLM one?
So for the LLM one, there is no searching as such, because I mean that if you the RAG itself, the RAG pipeline that I had shown early on, that already searches for the. I'm just trying to go to that slide. So the RAG pipeline here itself, when these documents are retrieved, it also performs this approximate nearest neighbor search based on the embeddings. So we are not touching that. So once we know the query, the chunks that are going to be retrieved is exactly same as the vanilla RAG pipeline. We are just deciding that do we have a cache for these chunks and how good this cache is.
Okay, so pardon my ignorance. So how do you get to know whether you have that chunk cache? Like, is there some?
Yeah, so for that we keep a metadata. For all these chunks, let's say I have 100 chunks in my my knowledge base. For each chunk, if we have a cache, we keep a metadata that whether the chunk is cached. Also, the metadata is fine-grained, like how much of which tokens in the chunk needs recomputation. So we keep a very compressed metadata on the cache, and as well as if the cache is used, then which are the tokens that need to be recomputed. So that metadata is stored in memory. Yeah. But the size of the metadata is very small. Yeah.
So metadata will be containing the embeddings plus some additional information that you compute.
Yeah. So let's say the cache has these words, right? Let's say like the light scatters or something. Let's say that this is the cache, right? Sunlight scatters in, let's say the second one, blue light scatters the most, right? So when the RAG tells that this cache, this chunk should be used, we will find whether I have this green chunk cached. Now, after I find that this is cached, maybe I will find out which tokens, let's say words are tokens here, which tokens is heavily influenced by the chunks that came before it. For example, let's say I find the scatter is the token which was heavily influenced, and if I am using it in a new context, I need to recalculate the corresponding values for scatter. So then I will keep pointers that, okay, scatter is the token, this index is something that I need to calculate if I use. And I have this computation budget, so I'll dedicate that budget to find the, to recompute the only for the scatter, what would be the causal attention. I will skip the other computations.
Got it. Thank you.
Yeah. Yeah, so this is just our Adobe research page, and there are a lot of interesting works that are going on in Gen AI. So if you're interested, please take a look. And these are the two papers that I presented today. I think the archive version of this is yet to come, but it is in one of the first authors' GitHub. So you can search, or it will be coming up in this SIGMOD. And for any questions or further discussions, please feel free to drop me an email. My email ID is shubhrato.mitra@adobe.com. Yeah, you have a question? Or okay.
Thank you, Subrata, for an informative talk. I request the audience to ask you questions, if any.
Sure.
Okay, I guess there are no questions. I would like to end the meeting. Thanks again, Subrata. Thank you, everyone, for attending.